Hello and welcome to another tutorial. So this time around we are going to be taking a look at maths, and in particular some really handy and useful maths for game development purposes. Now, completely understand if the first reaction to this is, oh hell no, I don't want to have to look at maths. Maths is awful. Completely understand. A lot of the ways that we get taught maths is very abstract, and it's also hard to relate to why it's useful, and that can very easily make us think that we are never going to use it or that we aren't able to do it. And the reality is that we very much can do it. And I want to focus on maths that we use in games. And this is stuff that I use, I would say, probably on a weekly basis. I'm doing stuff like of this. And I want to focus on that, of stuff that's useful, stuff that we'll actually be using. And so there's going to be a little bit of explaining of stuff, and then we're going to look at some practical applications for things. So I said we're looking at trigonometry. And one of the things in general that we're working with this stuff, so I'm going to cover a few sort of fundamental basics of what we're talking about. So we're going to be working with angles. So looking at the angles between things. We have different ways of expressing angles. And we can see we've got this setup where we have the white sphere rotating around at different angles. And we can see at the top there, we've got the angle in degrees. And then below that, we've got the angle in radians. So this is one of the things that can really easily trip you up. There's two different ways, there's actually a few different ways of expressing angles, different units for them. Just like how, we can express distances in meters, or it could be in feet, inches, yards. So we've got different ways of expressing things. That's the same case with angles. And just like with those units, there's a conversion between them. So angles, the version that is generally very human-friendly for being able to look at, unless you've worked with a lot, is degrees. Degrees is something that we can generally understand fairly straight, intuitively. Something that's directly in front of us, that's 0 degrees, and we're often measuring from in front of us, so 0 degrees. Directly to my side is going to be 90. Directly to my left would be minus 90, or 270 degrees, and directly behind me would be 180 degrees. So degrees is a really handy one when you want people to be able to visualize it, when you want people to be able to enter numbers. So it's why if you're setting up stuff in an inspector for people to be able to tune, if it's something that's angle-based, I really recommend degrees. If it's a speed, degrees per second. So that's what I've done here with the angular speed. That's degrees per second. But if I was specifying the angles for things, I would generally always go for degrees. It's a lot easier to work with. The other one that we've got is radians. So radians is what a lot of the math functions that we use expect as their input. Now, some of the maths functions have good documentation and description, so it's very clear what they actually use. Other ones don't. And with the way angles work, it can at times be difficult to tell that you've got the units wrong. So that's one of the most common things that you can run into, is having the units wrong there and it being in degrees when it expected radians. Now, a full circle is 360 degrees, or in radians, ends up being about 6.28. But that is 2 times what we call a constant called pi. So 2 times pi. And pi has a very specific value you can access. You don't need to remember exactly what it is, but it's roughly 3.14 and then a lot after that. And it is something that we can, in any of the Unity, Unreal, any programming tool that we're using, we do have direct access to the value for that, so we don't need to remember it. We just need to know that it's used in things like the conversion to degrees or from degrees to radians, so it's how we use it there. So trigonometry, we're working with angles, and we're working with angles in particular in relation to right-angled triangles. So what we see here, if I pause this, all of the triangles that this is generating over its entire period are all right-angled ones. So a right angle means something that has an angle that is 90 degrees. So we have here this right-angled triangle. It's 90 degrees. We have a couple of other parts to that then that we can define. The longest side here is what's known as the hypotenuse. And then depending upon where we're measuring our angle from, in this case, I'm measuring the angle from our forward direction. That means we have our red one here that's horizontal is our adjacent value, and our vertical one is the opposite value. So there is actually a relationship between all of these. So when it is a right-angled triangle, if we know an angle and a side, we can figure out pretty much anything then. We can figure out the lengths of other sides, we can figure out the other angles, because we know one of them has to be 90, so if we know one other one, then that gives us all the information we need to work out everything for it. And what that lets us do, and actually I'm using that here, one of the most common things we'll do with that ability to determine the locations of things is what I'm actually doing here for how I'm positioning this sphere that is moving around. Because its hypotenuse always stays exactly the same. That doesn't change. And that actual moving sphere, I'm not doing it by rotating it, I am actually changing the position of it. And I'm calculating that position by figuring out what these opposite and adjacent values are. Let's take a look at how this is actually doing the moving around. Because as I said, what we're doing is we've got the hypotenuse here is fixed, and then as the angle changes, I'm actually calculating these opposite and adjacent values. So let's take a look at what I'm doing here. And here is where it is actually happening on these two lines. So we have a few mathematical functions. One of them is sine, aka it's just often written as sin. So sine, the maths behind that is sine of angle is equal to our opposite divided by hypotenuse. So that's what we're doing here. So if I take this and reorganize it, I can actually say that opposite is equal to sine of the angle multiplied by the hypotenuse. And that's the maths that I'm doing here. That angle, which we can see, here's how in Unity I convert it from degrees to radians, multiplied by our hypotenuse, our orbit distance. So sine is when we're working with the side opposite to the angle that we have. If we're working with the side that is next to it, that's where we use cosine, also known as cos. Now the way it works is that cosine of the angle, and just so it doesn't look like it's a subtraction, I'll do it this way. So now cosine of the angle is adjacent divided by hypotenuse. Or the other way we can write that is that adjacent is equal to cosine of the angle multiplied by hypotenuse. So if we have an angle and we have a distance, we can figure out the opposite and adjacent sides. So we can figure out the position of something relative to where we are. And that's what I'm doing with this. As it's continually sweeping around, it's calculating the opposite and adjacent, the cosine and the sine values, and using that to set the position of it, which we can see it sets the position here. So it calculates the adjacent and opposite, and then it applies those. And these change in a very predictable manner. Sine and cosine have a very particular pattern, and you can see I'm actually graphing it here. So they have this, essentially this wave. So they follow this pattern, and it repeats continually. If we go for an angle that is larger than 360 degrees, that's actually okay. So anything that is more than 360 degrees, we can just keep subtracting 360 from it while it's still above 360, and that will give us what the actual effective angle is. So cosine of 10 degrees is exactly the same as cosine of 370 degrees. So anything where it's a 360 degree difference from it is exactly the same. And sine and cosine both follow this exact same pattern. What we would say is that they are out of phase with each other. So it's the same cycle over the same duration, so 360 degrees. So it follows that same cycle, but one is offset compared to the other. And this is actually really useful for us if we want to have stuff move. So being able to make something bounce, which pickups in the world, you'll sometimes see things like that bounce to draw attention to them. Sine and cosine are a really easy way of doing that and having that move quite smoothly. So they're very, very handy for that. So we can use them for positioning things like we're doing. We can use them for being able to make things move at particular rates. So there's a lot of things that we can actually be doing there with them. So let's dive in and actually start doing some of those things. So I have another scene here. And what we're going to do is that we have this spawner. And I've got a couple of things here, a prefab that it's going to spawn. And I want to have some options here in terms of the mode that it spawns in. So I want to be able to have an option for spawning a fixed number of them, which I'm going to switch it to that for now. And I also want to have support for being able to have it spawn them, and it's adaptive. The number is based upon the distance to try and have a fairly even spacing. And so again, we're going to be making use of sine and cosine and those different aspects of trigonometry to make this work. Then we're going to add some cool effects to it. So let's take a look at what we already have for the spawner. So I've already got a bit of infrastructure here. I've got stuff that handles maintaining that list of spawned objects. It works out if it needs to spawn new ones. It works out if it needs to destroy ones. So that's something where we don't need to think about that. That's already taken care of. So we are just going to focus on implementing the key bits that we need to for this. So, okay. We want to figure out how many we are going to actually have from a spawning point of view. So, okay, let's look at then, with this, I need to check the spawn mode so that we're not going to sort of dive into too much detail on that. But if it's a fixed number, then expected number of objects is going to be equal to num to spawn. Where it gets a little bit more interesting is otherwise. So otherwise, it's trying to maintain a fixed distance between them. And it's trying to do that as best fit as it can be. Now, we've got a circle. So if we want to have things spaced at a set amount on that circle, we need to know the area that we've got to spawn in. We need to know essentially the length of the outside of that circle, something that's known as the circumference of the circle. So what I would do is I would first figure out the circumference. And for that, well, I need to know the radius of the circle, which I don't have that here as an option yet. So I'm going to set up, so we have serialize field, float, and our spawn distance, which is our radius. So we're going to set that to, we'll go for 5 initially. So circumference, well, there's a very specific way we calculate this. It is 2 multiplied by the radius and multiplied by pi. So that gives us our circumference. Now we have an approximate spacing. So what I would say then is our expected number of objects. Well, that is our circumference divided by our approximate spacing. And I'm going to make it that it just rounds to the nearest integer. So it might be a slightly larger spacing, it might be a slightly smaller spacing, but it's going to be as close as it possibly can be to where it needs to be. So, okay, we've figured out the spacing there, we've got this. Now the destroying, the adding, all of that is happening. All we need to do is position the objects. So position all the spawned objects. So we've handled the instantiation, everything like that. We're just placing them where we need to. And we already know sine and cosine can be used for this. So, okay, I need to know what the angle between all of these is, because I know I've got 360 degrees. I know the number that I'm wanting to spawn. So the angle increment, the angle between the different ones, that is going to be our full size of the circle, so the full angle. Now, because we're using sine and cosine and they use radians, just to save an extra conversion, I'm using the radian version of what the full angle would be for a circle, which is 2 pi. So we take that and we divide that by, we can actually, rather than expected num objects, we'll use spawned objects dot count. Not that there should be any difference, but it just ensures we're using exactly that. So, okay, we've got our angle increment in radians. Then what I would do is index is 0, index is less than that. So, okay, we can work out the angle to spawn it at. So angle to spawn at, that's going to be our index multiplied by the angle increment. So we'll start at 0, and then we'll keep stepping at that increment all the way around until we've spawned all of the particular ones. We have our distance to spawn at is our spawn distance. Now, I wouldn't normally set up another variable here, but there is a very particular reason why I am doing that, which we'll see with some of the things we add in later. So I can work out my position is a new vector 3, and what I have is, okay, I want our math f sine angle to spawn at, and as we did with the multiplying by hypotenuse, that's our distance to spawn at. And autocomplete has gone quite wrong there. We then, because we're not moving them up in the air, we have that at 0. And then we have math f cos angle to spawn at multiplied by the distance. So that's good. We've worked out where this should be positioned. So we can go spawned objects, and that transform, but we'll do, rather than position, local position. So that's good. We've set the position there for it. that should mean that we have a bunch of objects being spawned with this. So let's run it. So we can see we've got them being spawned. Now we're spawning a fixed number. And the downside with that is as we change the radius, they move further out, but we don't get the same sort of density. If I change that to approximate spacing, then that works out much, much better. As we get to smaller and smaller distances, we have fewer objects. So that's pretty cool. We've got these things spawning, and we've got them appearing at locations we need in the world. So really handy for scattering things around. But we can do more than that with sine and cosine. I mentioned before that one of the things that's really handy with them is if you want to have something bounce, because as we saw here, there is a fixed predictable pattern that this follows, and that pattern repeats. And it's a nice gradual change, so it makes it really ideal for having just a very gentle bouncing happening there. So, okay, we want to use that for actually making the bouncing happen. Now, what I've done is the prefab already has a script on it. And so we've largely got everything we need. So we've got stuff running for updating the bouncing. I'm passing in time, so here it's going to do the actual positioning logic. So we're going to get that up and running now. Okay, so the first thing we need to be able to do is we want to be able to control how fast we're bouncing. Now, for the scene where we're rotating here, this one, it kind of made sense for being able to specify the speed here in degrees per second. That way then it's a more fairly intuitive for something like of this. It worked out a lot better. But that's not always the best option. So there's a couple of key things that we need to know in terms of being able to control these speeds the way we talk about and describe them. So sine and cosine follow this consistent pattern, and they do that over what's called a cycle. So this from here to here is a full cycle, and then it repeats exactly. The time from the start to the end of a cycle is what we refer to as the period of it. That's measured generally in seconds. So period can be an okay thing for being able to set, but I find, and this might just be me, I find that period is not always as intuitive a thing for setting. What I generally use is you have also something called frequency. So whereas period is how long a cycle takes in seconds, the frequency is how many cycles happen per second, which is generally, we use the unit hertz there for it, Hz. And you might have seen it with listing frequencies of things. So radio stations, modems, things like of that, Wi-Fi, different ones like of that. You'll see frequency used there. So the frequency I find is a bit more of an intuitive one of, I want this to happen twice a second, or I want this to happen, only half of it complete within a second. So I find frequency is a little bit easier to work with. It's very easy to convert between the two of them because the period is 1 divided by the frequency, and frequency is 1 divided by the period. So they're very easy to actually work and flip between. So if you find that period is a bit more of an intuitive one for you, then that's an easy one to use and easy to do any of the conversions you might need to. So in terms of what this is going to do, well, I want to be able to control the bounce frequency. So bounce frequency, which I'm going to default to 0.5. So that should mean it will complete half a cycle in a second. I want the bounce height, so how high it moves. We'll say that that is 1. And I also need to keep track of the current time. So what I will do is here, first thing, current time, and we add delta time to it. So the reason I pass it in here is so that if I wanted to scale up how fast time is going and do different things for different objects, then I can easily go and adjust that. So that's why I tend to not use time.delta time except at the very top level of running these functions. I find it just makes things a little bit easier if I'm doing fancy effects later on. So, okay, we want something to be doing that bouncing. So first thing I need to do is work out where we're at in that curve. So what I would do is our current time. Now I want it to be that it takes 1 second to complete a single cycle by default. So we know that sine and cosine repeat over 360 degrees or 2 pi. So if I take the current time and I multiply it by, and I'll do it in this order so it's a little bit more obvious. So current time by 2 times pi. That means 1 second, this would evaluate to 2 pi, which would mean it would have completed a full cycle. And every multiple of a second after that will be a full cycle. Then what I would do to use the frequency is just multiply like that. Then our height offset ends up becoming our bounce height multiplied by that. So now we know the height offset for it. And then I can just go, well, bounce mesh, game object, and I can set its transform local position is a vector 3 up by the height offset. What that should mean is that all of these objects that are bouncing, and we should see, so they bounce perfectly in sync, and we can see if I adjust that frequency, so if I ramp that up, they'll bounce really quickly. And if I really lower that, they will bounce very, very slowly. So slowly, we can't really even see them moving with that. Let's make it not quite as ridiculously slow. You can see very slow movement there. But they all move in sync, which isn't great. We want to be able to actually split them up. We want to be able to offset them. So when we've got something with this like this, where we've got a wave and we're offsetting it, we're talking about the phase of it. So sine and cosine, we saw they were essentially the same curve, just shifted. They were 90 degrees out of phase. So we could give a phase value to each of these things that are spawned. So I'm going to give here phase is 0. I'm going to set up a public void set phase and new phase. So just storing it, we're not doing anything too complicated. And I will do current time equals 0 whenever we set it. And then to apply the phase, well, what I would do is angle. I'm going to bring all of this out so it's not too unwieldy. So we do that. So we have angle plus our phase. So what that now means is that each of these will move according to that particular angle and that phase. So we can offset the individual ones scattered around. Now the actual offset that we need is pretty straightforward. Now to avoid, because I'm not writing, this is going to be not amazing code for performance. We wouldn't normally be doing this regeneration and all this stuff every time. So what I will do is I will go spawned objects, index, and I want to get component, and I want to get our bounce helper, and tell it set phase, and we just give it the angle to spawn at. But I specifically want to check, okay, was the object list changed? Just because otherwise it gets something where we're doing a get component a lot, which is not ideal. So let's test this out. They should now move at a different phase. And it looks as if they are rotating in a coordinated manner, but they're actually not. Each one is doing its own calculations independently. It's just that because of the settings of how it's working, it gives the impression that they're moving in a coordinated way. So now I'm going to go a little bit further. And what I want to do is I actually am going to set up a multiplier for the phase. So we're going to have phase multiplier. And because it's something where we will be messing with it, I'm going to have a cached phase multiplier, which then what I will do is down here. So if the object list has changed, we want to update stuff, or if phase multiplier is not equal to the cached version. And we do that by phase multiplier. So now we can have them be scaled up to be appearing at quite different phases. So not just being that smooth rotation. So let's see what that looks like. So we've got a phase multiplier of 1. If we go to 2, we have essentially 2 full cycles of the wave happening. And every even number, well, every whole number is going to add an additional cycle. So this multiplier is essentially how many cycles are there in this. And it ends up looking quite cool as we start to do things like increasing the distance. Now it does a pretty good job there. And so we've got some pretty cool looking effects there. We can go a little bit further, because we've done some cool stuff there, but there's a couple of other things that want to really add into this. So I'm going to actually set up so we can vary the distance that these things spawn at. So what I'm going to have here is serialize field float distance variation. And we'll default that to 0.5 meters. So the idea being is that where it spawns, it can be 0.5 meter in or out from that. I'm going to make it so I can control the frequency of that. So distance variation frequency, which I'll default initially to 0. So there's no changes being applied to it. So what I can then do is my distance to spawn at, we take that spawn distance there, and what I do is I add to it my distance variation multiplied by mathf sine, and we use the angle to spawn at multiplied by the distance variation frequency. So this is going to vary that distance in and out on the curve as we move around it. So that's going to give us a bit of an adjustment there to the locations. And that's why I had this angle to spawn at and distance to spawn at as separate things. So let's see what that looks like. We'll go for approximate spacing. We'll move things out about 10 meters, and that looks okay. So they will all be moving around like that. So, okay, so far so good. If the distance variation frequency here, let's set that to 1. So don't see a huge change. But as we start to add to this, we get more of a variation happening. We can increase the distance. If we then also combine that with updating the phase, we start to get things where, if we go to the scene view, we've created now essentially some really interesting patterns. So we're not limited just to positioning things in a circle. We can be doing quite a range of different sort of patterns here. And it ends up resulting in really cool sort of things that we can create. So sine and cosine, trigonometry, angles, all of these things, they're incredibly useful for doing interesting things in games. We can position stuff in a regular way. And with a few little tweaks, we can make that so that that's actually quite an intricate sort of pattern of spirals, things like that it effectively creates. We can make things bounce for then drawing attention to them, and we can control the speed that they're doing that at. So it gives us a lot of options for being able to do some really cool elements in the world. Position things, so spawning things in a radius around someone, or having things where these could all be doing little particle effects, things like that. You've got a lot of different things that you can be doing there with these, and the angles are our tool for that. And that's one of the things I always say with maths, is maths in particular, when we're talking about it in the games context, maths is a tool. And you don't need to love maths at all. You don't need to love it. It's about knowing how to use the tool. And that's the key thing with it, is finding practical applications for it, finding things where you can use it. So sine, cosine, positioning, making stuff do things at a regular pattern, cycling between things, that is stuff that working with those enables you to do them quite easily. So I really encourage diving in and experimenting with this. Try different frequencies, different things like that. You could add on particle effects. You could add on stuff where these are all connected to that spawner. So if I started rotating this, then we have a sequence of these rotating around you. So you could start to really create some very interesting effects there, of vortices around a player. You can imagine that as sort of a bit of an aura around the player. You could be using things like this for that. So experiment with it. You're not going to break anything. And if you do, it's an opportunity to learn how to fix it. And you'll have the reference version of the code to refer back to. But experiment with it. Get a bit of a feel for how these work, how the different terms work. Try and set up your own idea for stuff. If there's different things you want to do for spawning, try that out and see what you can actually create with that. Thanks, folks. Hope you found the video interesting and helpful. If you have, chuck in a like and subscribe. It really helps out. It's really appreciated. If you've got any questions, chuck in a comment below. If there's other things you'd like to see, other areas of maths you'd like me to talk about, or more on this you'd like to see, then chuck those in a comment as well. If you're looking for the code for the project, the code is available up on GitHub, and I've placed a link to that in the description below. And if you are looking for other ways to support the channel, I do have a Patreon, and there is a link to that in the description as well also. But until next time,